Welcome to the Explainer. Today we're diving into something called CRYSTALLIS. Now this is a rigorously falsifiable research program for physical learning. And honestly, it's a completely fascinating look at how we might rethink computing and memory from the ground up, not with traditional software, but through the raw physics of materials themselves.
So, right off the bat, let's dive into the core question driving all this. Can a physical network actually learn? Can matter do more than just, passively respond to a signal? What we're exploring here is whether a physical network can preserve a fading trace of its own recent activity and then actually use that trace to alter what happens next. It's a wild concept.
But before we get carried away, we really need to establish exactly what CRYSTALLIS is, because we have to strip away all that sci-fi hype about magical self-learning matter or conscious AI entities. Right? CRYSTALLIS is simply a scientifically conservative, highly testable architecture for local physical learning. It's a working hypothesis. It proposes a very specific, grounded mechanism for how physical elements could adapt over time.
Okay, here's our roadmap for today's explainer. We're going to hit 6 key areas: the working hypothesis, crown and root timescales, the 4 node families, the scientific lock, the experimental roadmap, and finally, the decisive question. Let's get right into it.
Section 1. The working hypothesis. Let's start with the central claim of this whole trace-to-latch architecture.
What's really crucial to grasp here is the explicit separation of functions in the causal chain. We're talking about a very specific trace-to-latch loop. It goes like this. Flow establishes a rhythm. That rhythm leaves a fading trace. Then a specific teaching condition gates that trace, and that gate creates a persistent latch. And finally, that latch changes future flow. So we aren't just waving our hands and saying, heat becomes memory. No, this requires distinct, measurable physical steps.
To keep things strictly scientific, the researchers use what they call the BOTS framework. Basically, every single time a claim about physical learning is made, we must be able to answer 4 questions. Boundary: what drives or constrains the system? Observable: what state are we actually measuring? Teaching condition: what supplies the update direction to make it useful rather than just arbitrary? And state change: what actually persists and changes the next response? If literally any one of these variables is missing, the learning claim is just scientifically foggy. It's incomplete.
Moving on to Section 2, crown and root timescales. To really understand how this system functions without a traditional central processor running the show, we need to look at these 2 distinct physical timescales. So, CRYSTALLIS separates computation into these 2 layers. You have the fast crown and the slow root. The crown executes what the system is doing right now, responding instantly. Maybe that's a voltage spike or an optical field. It's immediate physical computation. Meanwhile, the root handles the slower transient and persistent states. It holds that fading trace of recent activity. The fast response has to settle before the root's fading trace totally disappears. So the crown is the now, and the root is the memory of what just happened.
Section 3, the 4 node families. Let's see how these timescales actually build into a physical grammar.
This breaks down the architecture without relying on any messy metaphors. You've got space nodes, which track where the excitation is right now. You've got time nodes, which hold that fading trace of what was active recently. Continuity nodes, which measure what matched a prediction. And gravity nodes. Now, actually, scratch that. I need to clarify. Gravity here just names the persistent influence, like how strongly a particular route will influence the next time. It has absolutely nothing to do with gravitational physics.
Section 4, the scientific lock. This brings us to the absolute crux of this explainer. This is the safeguard that prevents us from mistaking just generic damage or heating for actual learning.
There's a foundational quote here. Dissipation says what happened, teaching supplies credit. Think about it. Heat, or energy dissipation, might tell us which parts of a network physically participated in an event, but heat alone has no semantic direction. It doesn't tell the system if that participation was actually, useful for a specific task. Because heat doesn't know it's useful, the architecture desperately requires a gate. There are 4 scientifically defensible teaching conditions that can supply this credit. It could be a contrastive gate comparing states, a reward-gated eligibility, a predictive mismatch, or a boundary-constrained objective. The main point is, without one of these explicit teaching conditions acting on that fading trace, the physical system might change, sure, but it definitely hasn't learned. And that brings up a really critical distinction in material science: memory versus learning. A material retaining charge because it was heated, that's a form of memory, like hysteresis. But
Remember, while every learned state is a memory, not every memory is useful learning. True learning means experience actually changes later performance relative to a specific objective. You absolutely need a task metric, a directional update, and strict controls.
Okay, Section 5, the experimental roadmap. So how do we physically prove this hypothesis works? Let's walk through the experimental gauntlet, which is especially important for strict metrology standards like those at NIST. To prove this claim, researchers propose starting with a simple, classical circuit. No exotic crystals just yet. There's a strict 5-step sequence: write, trace, gate, latch, and read. This sequence rigorously separates the fast state, the fading trace, the teaching gate, and the persistent latch into distinctly measurable steps. You literally have to measure the trace decaying and then prove that the gate only modifies the specific sites that still have an active trace.
And to validate those steps, you need brutal experimental controls. For instance, you have to run a test with equal deposited energy, but with completely scrambled timing. Why? Well, if the retained update can be explained entirely by cumulative energy, just generic heating, instead of the exact sequence and timing of the trace in the gate, then the whole trace-to-latch hypothesis completely fails its test. It's a strict lock.
We also need to be scientifically conservative when it comes to advanced materials like diamond and discrete time crystals, or DTCs. You might hear them hyped up in relation to this, but let's de-hype for a second. Diamond defects are incredible. Calibrated local probes, they sense what's happening locally with brilliant precision. And time crystals offer these robust temporal rhythms, but they are not necessarily the adaptive memory itself yet. Time crystals do not learn by themselves. They are entirely optional for this architecture. The core classical trace-to-latch physics must be proven first.
Finally, Section 6, the decisive question. This brings us to framing the ultimate position for this whole research program. We really want to drive this home. We are not asking if matter is sentient. We aren't asking if crystals possess magic. We are asking a highly specific, falsifiable physics question. Can a driven physical network convert a fading physical record of its own participation into a bounded, useful coupling change governed strictly by a task-dependent gate? Falsification is the absolute bedrock of this research. The hypothesis demands that the retained update must follow temporal eligibility multiplied by teaching, not just cumulative energy alone. If a simpler, conventional circuit can perform the exact same function without these distinct, separable steps, then CRYSTALLIS hasn't earned a separate claim. It's that simple.
And that leads to the decisive question the developers of CRYSTALLIS are bringing directly to the physics and metrology community. Simply put, what is the smallest trace-to-latch experiment worth doing? What specific measurement makes this incredible claim credible, and exactly what result completely kills it?
I want to leave you with this final thought which perfectly summarizes the entire architecture. Flow alone makes a path. Credit decides whether the path should remain. A physical flow might make a temporary mark, but only a defined credit decides if that mark becomes a permanent, learned pathway. So, what do you think? Are we on the verge of a completely new physical grammar for computing? Thank you for joining me on this explainer. Let's keep demanding rigorous experimental proof for the future of physical learning.